Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and the need to address their potential risks and ethical issues. As LLMs become more capable and widely used, we must pay attention to their vulnerability to adversarial prompts, inputs designed to exploit their weaknesses, which can result in unsafe or biased outputs. To ensure the safe use of LLMs, we need to identify and mitigate these vulnerabilities. One effective method for uncovering these weaknesses is red teaming, where human testers simulate attacks on the model. However, this manual approach can be resource-heavy and may not catch all possible vulnerabilities. To overcome these limitations, automated red teaming has been developed. This method uses an LLM to create adversarial prompts for another LLM, allowing for quicker identification of risks without human involvement. Despite its efficiency, automated red teaming often focuses on optimizing specific prompts or uses a fixed attack style, which can limit the diversity of prompts and reduce its effectiveness. Rainbow teaming addresses this by treating the task as a quality diversity search, refining a set of seed prompts to enhance both their quality and diversity. However, this process can be slow, especially without a well-tuned model to guide the changes. To improve the balance between efficiency and diversity in red teaming, we introduce FERRET. This framework enhances rainbow teaming by generating multiple variations of prompts in each iteration and using a scoring function to rank these variations based on their harmfulness and diversity. Each iteration of FERRET consists of 4 steps: sampling, mutation, categorical filtering, and scoring. We start with an archive of harmless prompts and use them to generate better adversarial prompts. In the sampling step, we select a prompt from the archive and use it as a reference to create a new prompt with a different feature descriptor. The selection of this descriptor is based on the effectiveness of the current prompt, measured by a fitness score. If a prompt has a lower fitness score, its feature descriptor is more likely to be chosen. Overall, our approach with FERRET significantly enhances the quality diversity search, reducing the time needed to achieve high attack success rates compared to rainbow teaming. Section Summary. In this section, we discuss the development of FERRET, an automated red teaming framework that enhances the rainbow teaming approach by generating multiple adversarial prompts in each iteration and employing a scoring function to optimize for both harmfulness and diversity. This method significantly improves the efficiency of identifying vulnerabilities in large language models, achieving higher attack success rates while reducing the time needed for effective prompt generation. Section: Step 2: Mutation. In this section, we describe our process for generating and evaluating candidate prompts through a series of steps. First, during the mutation step, we take the sampled prompt and the risk and attack features to create multiple candidate prompts. We begin with risk mutation, where we adjust the original prompt to align with a specific risk feature. Next, we enhance these prompts by incorporating the attack style, resulting in a set of candidate prompts. To ensure variety, we filter out prompts that are too similar to the original by measuring their similarity using a blue score. In the next step, categorical filtering, we classify the candidate prompts into risk categories using a scoring function. We discard any prompts that do not match the target risk category established during mutation. This step is crucial because the models we use may not fully understand the risk categories, which could lead to irrelevant prompts. By keeping our prompts aligned with the risk categories, we enhance the diversity of our prompt archive. Following this, we move to the scoring phase. After filtering, we have a set of candidate prompts, which we evaluate using a scoring function to determine their harmfulness. We select the prompt with the highest score and compare it to the existing prompt in our archive. If the new candidate is deemed more harmful, we replace the old prompt with the new one, updating our archive. In our FERRET pipeline, we utilize large language models for 3 main tasks: mutation, categorical filtering, and scoring. We employ Mistral 7B for generating mutations and Llama Guard 2 for filtering prompts based on risk categories. For scoring, we explore 4 different functions. The first is Llama Guard 2 Fitness, which assesses the fitness of the mutations based on their likelihood of being classified as unsafe. The second, Mistral as judge, compares mutations against existing prompts to eliminate less effective ones and ranks the remaining options. The third combines both Mistral as judge and Llama Guard 2 fitness to refine our selection further. Lastly, we trained a reward model to evaluate the harmfulness of adversarial prompts, using a preference dataset created through our pipeline. In our experiments, we utilize Llama 2 Chat 7b and Llama 3 Instruct 8b as the target models for our adversarial prompts, with all prompts used throughout the framework detailed in the appendix. Section Summary. In this section, we describe our process for generating and refining candidate prompts through mutation, filtering, and scoring. We first mutate prompts to align with specific risk features and attack styles, then filter them based on categorical relevance and harmfulness, ultimately selecting the most effective prompts to update our archive. Section: Initialization of Archive. In this section, we initialize our archive by randomly selecting prompts from the Anthropic Harmless dataset. We define the archive's features using two dimensions: risk category and attack style. The risk categories include 11 out of 13 categories from the ML Commons AI Safety Taxonomy, supported by Llama Guard 2. For attack styles, we refer to the categories from Rainbow Teaming. A detailed list of these dimensions and the hyperparameters for training the archive can be found in the appendices. We conduct experiments on FERRET and compare it with two baseline methods, Rainbow Teaming and Rainbow Teaming with a category filter. We assess FERRET's performance in identifying adversarial prompts that provoke harmful responses. Rainbow Teaming involves 3 steps: sampling, mutation, and judging, without a categorical filter, generating 1 mutation per iteration. We use Mistral 7b as a judge to compare mutations with existing prompts in the archive. We ensure consistency in archive initialization across all baselines. For evaluation, we utilize 2 safety classifiers, Llama Guard 2 and GPT-4, to measure the attack success rate, ASR. Llama Guard 2 classifies attacks per category, while GPT-4 assesses whether a response is unsafe, regardless of categories. Our main results, presented in a table, show ASR comparisons across various risk categories using different frameworks on target models like Llama 2 Chat 7b and Llama 3 Instruct 8b. We calculate ASR values using both classifiers, organized by risk categories such as violent crimes and child sexual exploitation. We report ASR values for Rainbow Teaming and Rainbow Teaming with a category filter as baselines. We also explore different scoring functions for FERRET, including Llama Guard 2 Fitness and Mistral as judge. All variants of FERRET outperform the baselines in Llama Guard 2 ASR, consistently exceeding 94% ASR for both target models. For Llama 2 Chat 7b, FERRET achieves ASR scores of 100% for Llama Guard 2 Fitness, while the baseline methods reach only 49% and improve to 89% with a category filter. A similar trend is observed with Llama 3 Instruct 8b, where FERRET variants achieve ASR scores of 100% and 99%, compared to 60% and 92% for the baselines. We notice consistent performance across risk categories, with the lowest ASR for Llama Guard 2 being 70% in the violent crimes category for Llama 3 Instruct 8b. The variant excels in specialized categories, significantly outperforming other variants and the baseline methods. For instance, in the critical child sexual exploitation category, the variant achieves 100% ASR on both models, while Rainbow Teaming struggles with 0% and 40% ASR. Even with a category filter, Rainbow Teaming only reaches 80% and 40% ASR on these models. Section Summary. In this section, we initialize our archive using prompts from the Anthropic Harmless dataset, categorizing them by risk category and attack style, and compare our method, FERRET, against baseline methods like Rainbow Teaming. Our results show that all variants of FERRET significantly outperform the baselines in attack success rate, ASR, achieving over 94% OSR across various risk categories and target models, particularly excelling in critical areas such as child sexual exploitation. Section: Reward Model Scoring Function shows greater alignment with Llama Guard 2 and GPT-4 OSR. In this section, we highlight the effectiveness of our reward model as a scoring function, which shows strong attack success rates in both Llama Guard 2 and GPT-4 evaluations. For instance, when we target Llama 2 Chat 7b, our reward model achieves a success rate of 0.95 for both evaluations, demonstrating its reliability. For Llama 3 Instruct, the success rates are slightly lower at 0.94 with Llama Guard 2 and 0.89 with GPT-4, but they still show close alignment. In contrast, other versions of FERRET that use Llama Guard as a scoring function, like LGF, achieve a perfect success rate of 100% with Llama Guard 2 for both Llama 2 Chat 7b and Llama 3 Instruct 8b. However, when we evaluate LGF with GPT-4, the success rates drop to 78% and 76%, respectively, suggesting that LGF may be too tailored to Llama Guard 2, which limits its effectiveness with other metrics like GPT-4. We also discuss the challenges faced by rainbow teaming in aligning risk categories, as evidenced by the significant differences between Llama Guard 2 and GPT-4 success rates. For example, targeting Llama 2 Chat 7b, rainbow teaming achieves a success rate of 49% with Llama Guard 2, compared to 92% with GPT-4, resulting in a 43% gap. A similar pattern occurs with Llama 3 Instruct 8b, where we see a 30% difference. This issue partly arises from using a smaller model as the mutator. To improve alignment, we introduced a category filter, CF, into our baseline. Our experiments show that rainbow teaming with CF performs better, achieving 89% with Llama Guard 2 and 81% with GPT-4 for Llama 2 Chat 7b, and 92% with Llama Guard 2 and 80% with GPT-4 for Llama 3 Instruct 8b. Regarding training time, we compare rainbow teaming with CF and FERRET to see how quickly they reach specific success rate thresholds across different evaluations. We set 4 thresholds at intervals of 0.05, based on the peak success rate of the weaker method for fairness. Our results indicate that FERRET significantly speeds up the initial stages of training, achieving the first threshold 44.6% faster in Llama Guard 2 and 58.3% faster in GPT-4. Although the speed advantage decreases later, FERRET still reaches the final threshold 15.2% faster in Llama Guard 2 and 5.5% faster in GPT-4. Interestingly, for Llama Guard 3, FERRET shows a 67.1% reduction in time to the first threshold, increasing to 82.5% at the last threshold, as it converges to peak performance much quicker than rainbow teaming with CF. Finally, we explore the transferability of adversarial prompts generated by our models. We assess whether these prompts can be effectively used on larger models that were not the original targets. By generating adversarial prompts with smaller models, we can save computational resources. We evaluate the transferability of the highest success rate archive generated by FERRET and 2 baselines across different target models. Our findings show that FERRET outperforms both versions of rainbow teaming in average transferability, achieving an average success rate of 51% compared to 0.35% and 0.47%, respectively. Notably, FERRET achieves 62% on Llama 3 Instruct 70b and 50% on GPT-4, indicating that the adversarial prompts generated can enhance the safety and robustness of larger models. Section Summary. In this section, we demonstrate that our reward model scoring function shows strong alignment with Llama Guard 2 and GPT-4, achieving high attack success rates, OSR, across various models, while also highlighting the challenges faced by rainbow teaming in aligning risk categories, which we address with a category filter for improved performance. Additionally, we find that FERRET significantly accelerates training time compared to rainbow teaming and exhibits superior transferability of adversarial prompts, enhancing the robustness of larger models. Section: Size of reward model, ERM. In this section, we examine the size of the reward model, ERM. We compare the OSR for FERRET using various base models, specifically QWEN 1.5 to 0.5b, GEMMA 2b, PHI2, and Llama 3 to 8b. Our findings indicate that the peak OSR tends to rise with the size of the reward model, achieving peak OSR values of 84%, 90%, 89%, and 95% for the respective models. While medium-sized models like GEMMA 2b and PHI2 perform well initially, they reach a lower peak OSR compared to the larger Llama 3 to 8b model. Additionally, we observe that larger models reach their peak OSR in fewer iterations than smaller ones. Next, we analyze the effect of the number of mutations in each iteration on the OSR of FERRET. We vary the number of mutations from 1 to 5 and find that the OSR generally increases with both the number of mutations and iterations. For lower mutation counts, such as 1 and 2, the OSR rises gradually, while higher counts of 3, 4, and 5 show a quicker increase early on. Ultimately, the success rates for higher mutation counts converge around 94% as iterations progress, indicating diminishing returns after a certain point. We also discuss open-ended quality diversity search, which aims to create a wide range of high-performing solutions by combining existing ones, fostering ongoing innovation in complex problem areas. Rainbow teaming was the first to implement a quality diversity framework for discovering adversarial prompts, and Ruby teaming built on this by keeping a history of past prompts and critiques, aiding in the generation of more diverse and effective prompts. In terms of adversarial prompting, we focus on creating inputs that can manipulate or confuse large language models, LLMs, to expose their vulnerabilities or biases. Techniques used in these attacks include misspellings, foreign language prompts, or applying specific personas. Finally, we explore automated adversarial prompt generation, where algorithms are employed to create prompts that lead LLMs to produce harmful outputs. This process helps identify weaknesses in the models and enhances their resilience. One method involves using a red LLM to generate test cases for jailbreaking the target model, while another employs a white box technique that refines prompts through genetic algorithms and LLM mutations. Similar to iterative prompt refinement, methods like pair and tree of attacks with pruning also utilize LLMs to generate candidate prompts. Some existing studies leverage reward models to evaluate adversarial prompts based on their effects on the target model, as demonstrated in MART and DART, which, like FERRET, use reward models to gauge the harmfulness of prompts and incorporate them into a database.